Hello everyone and welcome back to another episode on complete reference to CUDA programming. So in previous episode, we have understood how launching multiple thread blocks can solve our problem of proper utilization of GPU resources. But we observed there is a problem with local thread IDs and we provided a solution by calculating the global thread IDs. So we have seen that presentation. Now let's try to modify our existing vector addition code so that it can handle multiple thread blocks and multiple thread blocks uh, inside the kernel. Also by calculating global ID, they'll be able to perform the vector addition, right? Now I'll be referring the same code again. So there are not many changes in memory allocation, the CPU function, then memory allocation on GPU, data copy, etc. There are only two points where we have to modify, that is while launching the kernel and inside the kernel, how we are going to perform the computations. Now, as I mentioned, we are going to launch multiple thread blocks. So we have to introduce some parameters here. So that is number of threads per block and number of thread blocks that I'm going to consider. So here number of thread blocks I'm going to consider 1024 and number of thread blocks will be calculated based on the input size. So here input size is 2 to the power 24 here, or rather I can say 2 is left shifted to 24 places, and that will be the number for the input size. Now question is I want to ensure that number of threads equal to n. So for that, what I'll do, number of blocks I'll define based on n and number of threads per block. So number of blocks, simply I'll say n divided by number of threads per block, and that will give me total number of blocks I am supposed to launch. As of now, don't pay attention on why I'm using this ceil function and why I'm using this typecasting to float for this number of threads per block variable. That will be covered in the next episode, because here, just to give you a brief idea, here n is that what we are considering is perfectly divisible by 1024, right? And that's the reason we don't need this ceil and this typecasting here, right? So here now this particular n by number of threads per block will give you total number of blocks. And now while launching the vector addition kernel, I'm using this vector addition kernel using many blocks kernel, and the first parameter I'm passing here is number of thread blocks, and this is where I calculated that value, and number of threads per block that I have defined here. Now if I change this value accordingly, let's say if I make it 512, accordingly this number of thread blocks will be changed, because it is a function of input size and number of threads per block. So let's say it is 1024, and rest of the things are again going to be the same. What are the parameters I'm passing? So this is the one point where we have to make changes. And now let's go back and see what is in the function definition here. So this is my kernel, and earlier we calculated the TID using thread_idx.x, but we know that this is not the right way to perform computation if we are launching multiple thread blocks. So I'll remove that. Now, as I mentioned, we have to calculate global ID. So to calculate that, I'll be using the same function thread_idx.x plus block_idx.x multiply by block_dim.x. This will give me global ID for every thread from any block, right? And simply I have to perform now, once I get the global ID, C of GID equal to A of GID plus B of GID, right? And this is just to guard from your invalid memory access, because sometimes it may be possible that you are launching many threads than required, right? So if you launch let's say by mistakenly number of threads which are greater than input size, right? Because C, A, B, those are arrays of size n, and if you launch more number of threads, those threads which is having the ID greater than n will try to access the variables or the arrays with that index, right? So for example, let's say your n is only 1024, that means array size is 1024, but unfortunately you launched more than that threads, right? So if you launch more than 1024 threads, what will happen? the GID will be greater than 1024, right? So GID, let's say for example it is 1028. Now the arrays are of size 1024, but the thread which is going to be having global ID 1028 will try to access C of 1028, right? But array size is of 1024 and the thread ID is 1028, that is accessing the invalid memory location or out of memory address it is trying to access. And in that case, your program will give either error or it will not give behave properly, right? And to do that, we are using that particular guard over there. Fine, that's the only changes you have to make in your program. And let's try to execute this program and try to see is there any performance improvement or not. Fine, so you can see now it is giving you the 65 times better performance. In earlier case, we launched only one block, and because of poor utilization of GPU, we observed the performance of only around 4 to 5 times better. But now I changed the program with global IDs and multiple blocks, and you can observe here now 65 times better performance I am able to achieve here. Now question is how those threads are getting scheduled. So you can see here total, this is my input size and those many threads I am launching, and blocks if you see it is approximately 32,000. Now question is how these 32,000 blocks will get scheduled. So again, let's visit our same logical diagram of how cores are organized on GPU. So in this case, we are having 32,000 number of blocks in our context. Now, as I mentioned in the previous episode, on every streaming multiprocessor, we have limit on how many threads can be executed at the same time. So let's assume that limit is 2048. That means at a time only 2048 threads are allowed maximum on this particular streaming multiprocessor. Now the block size I'm having here is 1024. So based on this, that means on this particular streaming multiprocessor, maximum I can launch 2 blocks, right? Now here 2 blocks are there, and now how many streaming multiprocessors I am having? So 16 streaming multiprocessors I am having, and every streaming multiprocessor with this configuration can launch only 2 thread blocks, right? And how many in total you can say blocks I can execute at a time? So 16 into 2, that is 32 blocks can be executed at the same time on this particular GPU. Now how many blocks I am launching here? 32,000, right? So given 32,000 number of blocks in my vector addition kernel, at a time on streaming multiprocessor I can launch only 32 blocks, right? 32 blocks, and each block is of size 1024, right? So now question is, these 32 blocks are scheduled, only 32 blocks are getting scheduled at a time. How these remaining blocks from this 32,000 blocks get scheduled? So idea is very simple. So out of all these 32,000 blocks, it will schedule first 32 blocks on wherever the streaming multiprocessor is free, right? So first 32 blocks get scheduled here. Once they complete execution, next lot of 32 threads, 32 blocks get scheduled on this streaming multiprocessor. Once it complete, the next thread block set of 32 blocks, and so on till all the blocks are completed its execution. Now you can see at any point of time while this kernel execution is happening, all streaming multiprocessors are getting utilized, because this streaming multiprocessor can handle only 2 thread blocks. Next it will be 2, next 2, and so on, right? So at any point of time, all the computing resources present on this GPU are being utilized, and which in turn gives us 100% utilization of your GPU resources, right? So that is the key takeaway from this particular episode. If you go on increasing number of blocks, it will ensure the proper utilization of your GPU resources. Now again, this particular approach is having some limitation, because in this case I assume the n, that is input size, is perfectly divisible by number of threads per block, and that's why we were getting number of blocks is n divided by number of threads per block is an integer value, right? So if it is perfectly divisible, we will launch exactly n number of threads, right? So if, for example, if I give in smaller example, if I'm having 16, that is my input size, and if I define threads per block as, let's suppose 8, then total number of blocks, which will give me 16 by 8 equal to 2, that is integer value. But what if I'm having this input is, let's say, which is not exactly divisible by 8, let's say I'm having here 20. Now if I do threads per block equal to 8, and number of blocks will be 20 by 8, and now here it will not be an integer division, right? So it will be 2.5 something, right? Now we cannot launch 2.5 number of thread blocks, right? So thread blocks must be integer value. So either I can launch 2 thread blocks or 3 thread blocks, but I cannot launch partial thread blocks, because inside the kernel the number of threads per block is going to be the same across every block, right? So this is the limitation of this approach. Now there are a couple of more challenges in this implementation that we'll be able to discuss in the next episode. Thank you.